Swayam Prabha. Digital India. Educated India.
Let us start this lecture with a thought process from Antoine Lavoisier, who says, "I consider nature a vast chemical laboratory in which all kinds of composition and decompositions are formed. Vegetation is the basic instrument the Creator uses to set all of our nature in motion." This is a very profound statement, and which is commensurate with Indian thoughts, the way they consider. And then it is important that we need to understand that and use it for the benefits of humanity. And in the last lecture, we basically discussed about how to handle the various chemical reactions and calculate heat of formation, heat of combustions, and heat of reactions. Of course, heat of reactions can be estimated by knowing the heat of formation, and heat of formation you can also calculate from the bond energy, right, and you can also estimate. So, today we will be discussing about how to determine the adiabatic temperature, and adiabatic temperature is very important because that will give you the ideal temperature whenever a combustion is taking place. So, the final temperature attained by a combustor under adiabatic condition is known as adiabatic temperature. We will consider same things, same system, that is a combustion chamber, and into which 1 mole of methane is entering, and along with 2 moles of oxygen it is reacting over in this control volume, and going to the product, that is carbon dioxide and water. We are assuming here the product is only the carbon dioxide and water. In real situation it need not to be, and here we are assuming it is an adiabatic. That means that no heat is transferred through the wall of this control volume, and the mixture is entering at 25 degrees Celsius and 0.1 megapascal. In this example, it need not be, it can be higher temperature, it can be higher pressure as well, and we will have to find out what will be the final temperature if no heat being transferred from the system boundary or through the system boundary, and that we need to find out. And for that we will have to basically invoke the first law of thermodynamics, considering the process to be steady process, and other one is a change in kinetic energy is 0, change in potential energy is 0, and then shaft work is not there, right, and it is adiabatic. So, considering these assumptions, we can invoke the first law of thermodynamics, which states that Hp is equal to Hr, that means total enthalpy of the reactant at, of course, the inlet temperature and pressure is same as that of the total enthalpy of the product. So, that is the thing, because from these equations we can get delta Hp. H will be equal to 0, that means Hp is equal to Hr, that you will get by invoking first law of thermodynamics for a control volume. And what is Hr? Hr is equal to summation of Ni Hi, and keep in mind this Hi is enthalpy is having two components. One is, this is your heat of formation of IS species, and this portion is basically sensible enthalpy, and this is Cp dt. Keep in mind that Cp of IS species is a function of temperature, and similarly Hp is equal to NiHi when I is equal to P, that means 1 to the product, and this is having both heat of formation and the heat of sensible enthalpy components, and of course we will use this thing in the this equation Hp is equal to Hr, and then we will find out basically adiabatic temperature. And at 298 Kelvin we know that H heat of reaction is equal to NiHFi minus NiFi naught. This is for the reactant, and this is for the product. This is for product, this is for reactant. So, this is your heat of formation, and these are basically heat of formation of IS species. And we can write down, this is sensible enthalpy, change in sensible enthalpy is nothing but your, for the product, Ni Cpi, this is unburnt temperature, and 2 T adiabatic, and Cp as I told is a function of temperature, and this is Ni integral of Cpi dt, and this is for reactants, and this is T naught, this is initial temperature, to unburnt temperature. That means before combustion this temperature will be, initial temperature will be different. If it is same like the in the present example, that is the ambient, it is same as the ambient temperature, then naturally this term will be 0 in the present examples, and that is equal to nothing but your heat of reaction, and this expression you can get basically from expression of Hp minus Hr is equal to 0. From this you can get this expression. This expression you can get here. And keep in mind that the Cp is a function of temperature, it can be polynomials, and A, B, C, these are coefficients, these are coefficients you can get from table, and these coefficients will be different for different species, and this goes on like maybe 5 coefficient polynomials or more even people are using. Now, keep in mind that Cp is varies with temperature. I have just shown you, this is a argon, helium, this is a monomolecules, this is a bimolecular, and this is a triatomic, this is a monoatomic molecule. This is biatomic or diatomic molecule, and this is a triatomic molecules. So, you can see that for monoatomic it does not change with respect to time, but the diatomic it is changing and it is not linear. So, therefore, you will have to fit it with the polynomials, and of course, the triatomic carbon dioxide whatever is a product which will be there all the time. So, therefore, triatomic. So, you will be it very clearly says that Cp is a function of temperature, particularly for diatomic and triatomic molecules. And if you look at these reactants is at the T naught and P, and then it will be basically heat of reactions which will be generated here. This is your heat of reactions, and the product will be provided will be going the same temperature, and this heat being utilized to enhance this product from T naught to T adiabatic, that is your adiabatic temperature, what we need to find out. Let us look at like how you can do that, and before doing that I must tell you it is very important that we need to know these products, right. For example, reactant of course we will be knowing, but the products we should know it beforehand, and product need not to be carbon dioxide and water for hydrocarbon and oxygen. It may be several other constituents like carbon monoxide, hydrogen, OH, radicals, other things. For that we need to basically look at the equilibrium products, otherwise the adiabatic temperature estimation won't be right. But in our example we will be using most of the time products which will be given. So, let us look at that effect of equivalence ratio on adiabatic flame temperature. As I told that this it will be dependent on the number of mole, it will be this adiabatic temperature will be dependent on the fuel air ratio or fuel oxidizer ratio of the initial mixtures. So, therefore, the adiabatic temperature will be dependent on the equivalence ratio which is shown. So, if TU is 300 Kelvin, that you will see that this is the line, this is basically the 300 Kelvin TU, and at equivalence ratio equal to 1 you will get a peak temperature. This is the peak temperature what you will be getting, around something maybe 2200 Kelvin, and this is your lean side, lean mixture, fuel lean, and this is your rich side mixture, and temperature drops down with the lean mixtures, and the temperature also drops down with the rich mixture, but the along the lean fuel lean side the drop down is much higher, rather in other words it is having a higher slope. And when the inlet temperature is basically 600 Kelvin or unburnt temperature, then naturally there will be increase in the temperature of the product. For the same equivalence ratio they will be having higher, like something maybe around 2350 Kelvin. And of course, both the lean side and rich side there will be difference, and difference on the rich side is little much higher as compared to the lean side, because of fact that there will be product which will be there. So, you can see this adiabatic temperature it will be occurring around maybe 1.05 the peak temperature or the maximum temperature, and with increase in inlet temperature from 300 Kelvin the curve is shifted upwards as I have told you earlier, and of course with the increase in adiabatic temperature. So, let us look at the adiabatic flame temperature of typical fuels at a stoichiometric mixture of various combinations. In the first two, what is being shown here in this table is methane air with same unburnt temperature or inlet temperature 300 Kelvin, but the pressure has been increased 0.1 to 2, it is something around 20 times, right, but the temperature increase is very small, something around 70 Kelvin, which is negligibly small. Now, if you compare this with that, like with this, like if you compare methane air for the same pressure, now the temperature has increased from 300 Kelvin to 600 Kelvin, but this is pressure is remaining constant, that you will find that is there is an increase in temperature from 2270 at 300 Kelvin of unburnt temperature to 2500 Kelvin when it increases to 600 Kelvin. So, therefore, there is a much increase in temperature. And if I compare with this one, both the things, methane air 0.1 atmosphere pressure, only difference is that instead of air I am using the oxygen here. So, you can find in place of 2200 Kelvin for methane air, the adiabatic temperature becomes basically 3030 Kelvin, which is much higher. That means oxygen plays a very important role, because nitrogen acts as a diluent and it takes all the lot of heat during the combustion. And of course, when I compare this methane air 300 Kelvin 0.1 megapascal, and you will find there is not much difference here. This is 2278 Kelvin, whereas methane air at the same condition it is 2200. Of course, the hydrogen air at 300 Kelvin 0.1, its temperature is quite high. Generally, it is considered to be around something 2400 Kelvin. And as we have already seen that that is basically the oxygen when it is when air is replaced by oxygen for the hydrogen fuel, the temperature again there will be increase in temperature. And of course, the carbon monoxide air, which is having a higher temperature as compared to the methane air, which is very surprising maybe for you people. So, that you keep in mind, and then we could see later on maybe the some of the propellants, what will be the temperature. Later on I will discuss. So, adiabatic temperature does not depend much on the nature of hydrocarbon fuel, as long as the oxidizer is air, and whenever the air is replaced by the oxygen, the temperature will be much higher, and the pressure does not affect the adiabatic temperature much. So, as I told you earlier that the chemical equilibrium is important. And what do you mean by equilibrium? Basically, if there is a mixture in a container, it will remain in the same condition unless otherwise you change the pressure or the temperature. That does not mean that if there is no chemical reactions. The chemical reaction will be going on, and however, the rate of forward reaction will be same as the backward reaction. For example, if I take 2 moles of hydrogen reacting with 1 mole of oxygen going to the product at 2 moles of water, and this is your forward reaction, right, and backward reaction I am showing over here. That means at the equilibrium you can say that rate of decomposition of hydrogen and oxygen to the converted into the water is same as the rate at which the water is decomposed into hydrogen and water. So, that the equilibrium is being maintained, or the chemical equilibrium being maintained. So, note that chemical composition will not change unless there is a change in pressure and temperature, as I told earlier. And how to find out the state of equilibrium is a question, because for finding out the adiabatic temperature we need to know the equilibrium product, and the equilibrium product and should be known, and also its mole fraction or the mass fraction should be known, such that we can get the adiabatic temperature. If for example, in this hydrogen oxygen system, product only need not to be water. It can be S2 hydrogen, and the product can also contain the oxygen, it can contain OH, it can contain H, it can contain several other things as well. So, therefore, all these constituents should be known properly to find out the adiabatic temperature, and unless you know the adiabatic temperature, you do not know really also the combustion product. So, this is a very complex process, one has to look at it, but question arises how to find out the state of chemical equilibrium, and to find out the direction of conversion of reactants we need to invoke the second law of thermodynamics. if you look at the change in entropy of system must be greater than equal to dq by T, that already we have seen. This is the second law of thermodynamics, and we state that chemical reaction proceeds only in the direction of increasing entropy. When there is a change in increase in entropy, then the process will move, otherwise no. However, from this equation, if the process is adiabatic, then entropy change becomes, change in entropy will be greater than equal to 0. So, one can find out the direction of process for an adiabatic system by considering the entropy increase or change in entropy. But if the system is not adiabatic, like case of combustion is taking place, we have to invoke the Gibbs free energy G, because entropy won't work. We know by definition G is equal to H minus Ts and dG is equal to dH minus Tds minus SdT. I am just differentiating this above equation, right, and H is equal to U plus Pv, that we know by definition. If I differentiate this, I will get dH is equal to du plus Pdv plus Vdp. At a constant and pressure and constant temperature, we will get basically this equation. If I will say this will be 0, and similarly here it will be 0. There won't be change in the temperature, there will be change in the pressure, because the pressure and temperature remain constant. And then dG you will get, basically if I can use U dPV here in place of dH, that is this portion I can put it here, and then I will get dG is equal to du plus Pdv minus ds. And we know from first law of thermodynamics, that is dq is equal to du plus Pdv, and we can use that thing in here, that is basically du plus Pdv. In place of this I can use basically dq. So, then I will get dz is equal to dq minus Tds. And keep in mind that as to the second law of thermodynamics, we know that Tds greater than equal to dq, because we know from here, right, and dq minus Tds is less than equal to 0. So, then we can say that dz is equal to dq minus Tds is less than equal to 0. What is the meaning of that? That is says that change in the Gibbs free energy at a particular temperature, pressure, and for certain number of moles will be less than equal to 0 for the process to occur, right. It should be less. So, therefore, the reaction will attain its chemical equilibrium only when Gibbs function attains the minimum value, that is change in the Gibbs free energy is equal to 0. So, if you look at this is basically, if I put this G over here and find out, like this will be something 100% reactant, and this I can say 100% product, and that will say the extent of the conversion. This says the extent of conversion. So, then it is possible, like in a Gibbs free energy will be changing, that means this is the minimum point, and that is the basically equilibrium composition or equilibrium component, and this point is dz is equal to 0, and this is dz is less than 0, and this is dz is greater than 0. So, this is the equilibrium composition what I will be getting, that means certain amount of reactant, certain amount of product. You can see from here the more amount of products will be at this point, and that we need to find it out. Let us now find out a procedure how to determine the equilibrium composition. As I told earlier that it is very important to know the temperature for finding out equilibrium, and to for finding out the temperature, we must also know the equilibrium combustion. For that, we will have to follow this procedure what I have enumerated here. First step is to identify the probable equilibrium species. For example, if I am considering hydrogen and oxygen system, so I can have probable species will be hydrogen, oxygen, O, H, OH, and water, and let us say this many or some more also may come. So, then we need to identify the equilibrium reaction scheme for example, hydrogen oxygen, and oxygen may react with H and then like that, and find out equilibrium constants that for each reactions, and strike a balance for elemental conservations that we will have to do, and strike overall mass conservations, and then we will have to find out minimization of Gibbs free energy and solve all these equations by iterative method. Mostly people use the Newton-Raphson method, but you may use some other numerical method for solving these equations. So, for an ideal gas mixture, Gibbs function of IS species is given by GIT is equal to GIT at 0. This is basically the Gibbs free energy at the standard state plus RUT ln Pi by P naught, and Pi is the partial pressure of IS species, and P naught is the standard pressure. So, of course, I have already told you that is Ru is the universal gas constant, and this is the Gibbs function of IS species standard condition at standard condition, and the Gibbs function for an ideal mixture will be G mixture will be NiGiR, right, and it will be, as I told, it will be two component. One is the Gibbs function at the of IS species at standard state, and this is the change due to the change in partial pressure or the mole fractions of the species. And at equilibrium, the dG will be equal to 0. That means, if I differentiate this equation, right, this equation, if I say this is 1 and this is 2 equation, then I will find out is nothing but dNi, that is change in the number of moles of species into the GIT naught and these terms that gives energy of them, and is plus the summation of Ni change in this energy, this gives function, and that will give, but you will find out that this change, because this is a constant, so therefore dGi T naught will be 0, this term will be 0, right. And you will also find out that change in ln Pi is equal to dPi by I is equal to 0. So, therefore, this term will be equal to 0. That means, since pressure is remaining constant, therefore, the change in the partial pressure of IS species will be 0, and then the dG mixture will be nothing but your change in the number of moles of species, summation of that over this is equal to 0. So, let us consider the A moles of species A reacting with B moles of species B going to the C moles of product C and D moles of product D, and the change in number of moles for each species will be dNA is equal to minus Ka, and where K is the proportionality constant, and similarly dNB is equal to minus Kb, and dNc is equal to Kc, and dNb is equal to Kd. So, this is from the law of mass action, and by using this we can substitute this above relations in the Gibbs function that we had derived, that is change in Gibbs, and we can put this thing over here, that is For the reactant side will be A, D N A if I consider, like A is equal to G I A T plus R U ln this is for the species A and this is for species B, and this is for the species C and then D. Now, what we will do, we will together put this gives function at the standard state for all the species together, and that is C G C T minus D G T this thing, and this is nothing but your change in the total gives free energy at the standard state is equal to, if I consider this thing into the right hand side, that is R U T ln P C by P naught into P D by P naught divided by P A by P naught P B by P naught. Keep in mind that these are all partial pressure of the species of the product side and this species of the reactant side. If I consider this as a constant, if you look at this as a constant K P, because this is the equilibrium constant based on the partial pressure, then I can write down delta Z T naught is equal to minus R U L T ln K P, right. This is a very important expression you should keep in mind, and of course, I can say that K P is equal to e power to the ln T is nothing but your this portion, right, I have already told. So, keep in mind that P I is nothing but Y I P, that already we have seen. This is your in terms of mole fractions, and then I can express this K P as in forms of the mole fraction, that is Y C power to the C C is your coefficient, stoichiometric coefficient, Y D divided by Y A Y B power to the B into P, this is your by P naught, because this is the pressure, this is the standard pressure, and this is the pressure of the pressure of combustion chamber. If it happens to same as the standard pressure, P is equal to P naught, then this will be 1, and if it is a different pressure, it may be these terms has to be considered also. So, keep in mind that if I know this K P and I can find out this mole fraction of the species, provided I know for this I should know the temperature, that means this temperature is known, this I can get from the table, the data, basically this data the standard gives a function from standard table, we can get this gives free energy from the standard table, and by knowing that, of course, you can get this delta G provided you know this coefficient of the reactions what we are considering. So, therefore, it is very important, that means the K P is a function of temperature, is dependent on that, and also this equilibrium space is also dependent on temperature. So, this means and also vice versa, that means this constituents the mass fraction of the space is also is dependent on the temperature, as I told earlier. So, we will consider an example, that is if carbon dioxide gas is heated to 3000 Kelvin at constant pressure of 0.2 megapascal, determine percentage of carbon dioxide that can be dissociated into carbon monoxide and oxygen during this process. So, at 3000 what is given here is 3000 Kelvin, temperature is given, but in real situation temperature is not known, you will have to guess it and then go on doing that, and pressure is of course must be known 0.2 megapascals, and we need to find out percentage of carbon dioxide dissociated during these reactions, and the reaction is carbon dioxide is going to the product of carbon monoxide and oxygen, and in this case the stoichiometric coefficient is 1 for the carbon dioxide, stoichiometric coefficient for carbon monoxide is 1 and oxygen it is half. So, according to ideal gas behavior for all component, equilibrium constant can be expressed as Kp is equal to YCO, this is coefficient power to the YCO, and Y oxygen power to the YO2 divided by YCO2 power to nu CO2, and P by P naught, and in this case keep in mind this is your 0.2 megapascal and whereas this is generally is 0.1 megapascal. So, therefore, it is something 2 is there, therefore, you cannot really neglect it. So, let x moles of carbon dioxide dissociated into CO, then what we will get? We will get 1 minus x CO2, that is the remaining, and YCO and ZO2 will be, that means these are unknown, these are unknown, these are unknown things, we need to find out this. So, we will have to do a C balance, because as I told you, we will have to do elementary balance 1 minus x plus y. So, if you look at this is cancel it out, this is nothing but y is equal to x, that is the things. And similarly, if I do O balance both the left hand side and the other side, you will find this is equal to 2 and this is 2 1 minus x, right, because oxygen carbon dioxide is there already from this equation, then y plus 2z, then if you simplify it you will get z is nothing but your x by 2, z is equal to x by 2. And total number of moles you should check it, because that is important to check whether you have done right or not. You will find total number of moles is 1 minus x plus y plus z, and that happens to be 1 plus x by 2 is equal to total n number of moles. Keep in mind that this is important because of fact that we will be expressing in terms of the mole fractions. So, therefore, the mole fractions is all given here, that is 1 minus x divided by 1 plus x by 2, this is here, that is the mole fraction, and x by 1 plus x by 2, and this is the mole fraction for oxygen. And now, what we will do, we will just put these things mole fractions, this is into this over here, this is basically YCO2 and this is YCO and this is YO2. So, we will substitute over in this expression, I can say this is equation 1, and then we will calculate how it will be. So, for that of course, we can find out these values as a delta G naught from the table, right, from table of Gibbs free energy at standard state, and of course, knowing these constituents, and then so of course, these things we know already. So, therefore, substituting values in the above equations, we can find out this is 494.948 and these mole fractions we are substituting over here, and then you can solve these equations, and this happens to be cubic equations, and it is not that easy to solve. You can use a iterative method or you can use some numerical method to solve this equation. By solving this equation iteratively, we can solving it by iteratively we can get x is equal to 0.8643, right. That means the percentage of carbon dioxide dissociated into CO is 8.643, and the rest of the things you can calculate very easily by just if I know these x values, and then I can find out what will be oxygen and what will be the carbon monoxide, all those things you can calculate easily. And that is the things what I am leaving for you to calculate and find out that sum should be equal to 100% or right. So, you will have to keep in mind or equal to 1 when you are considering the mole fractions or the okay. So, thank you very much. We can see in the next lecture about the ideal rocket engines and how to analyze by considering ideal flow in the rocket engine. Thank you very much.